Okay, welcome to Lecture 7 for ECE 203. Today we're going to look at Fourier series. So the course for the most part has been building towards this over the last few weeks, and I've said a number of times that we can represent any signal with a sum of sinusoidal functions. Okay? And in particular, we can represent them sum of sinusoidal functions with harmonically related frequencies. Okay, so to be specific, if we have a periodic signal, okay, then we can represent it as follows. Okay, so this first requirement, this if, right, this is just the definition of periodicity. So if the signal is periodic, right, and that just means we can write x of t as a sum as equal to x of t plus t naught for some t naught greater than 0, right? Where this is the period, this is the fundamental period. If we can write that, then the signal is periodic, right? And that has to hold for all values of t, for just one t naught. Okay, then we can represent the signal x of t as the sum of a number of harmonically related sinusoids. Okay, so the first one would be at a frequency of 0, right? That's just this A0. That's just the DC, or the constant term. And then we're adding to that a number, an infinite number, potentially infinite number of harmonically related sinusoids. Okay, each with different amplitude, right, and different phase. And what you'll notice here is that they're all integer multiples of this f naught, right, where f naught is the fundamental frequency. Okay, and f naught is related to t naught as follows. Okay, just like we're always used to, f naught equals 1 over t naught. Okay, and that's true for some specially chosen values of the AKs and pHs, right? We're somehow going to have to now design AK and pHk such that this representation is true. All right, so in this lecture we're going to talk about how we design those AKs and the pHks, and we're not going to use this representation where that I have written here. We're actually, of course, going to do this with complex exponentials, because it's actually going to simplify notation a lot, and hopefully that'll become pretty clear, and you guys will understand why we've looked at this complex representation for quite some time now. Okay, so if we were just to take this this equation here, right, and rewrite it using complex exponentials, we actually get this equation down here. And now we've taken, since if we expand cosine using Euler's identity, right, you get two exponential terms, one at a positive frequency and one at a negative frequency. So we've just changed this sum now to go from minus infinity to plus infinity. Okay, and then we've kind of changed the definition of the AKs, just like we saw before. We went from capital AK to lowercase ak. And then, of course, the complex exponential, right? And the things that are in the exponential are, of course, j, the imaginary number, 2 pi, k, that's the index of the harmonic, and f naught, right, fundamental frequency, and then, of course, time. All right, and this is known as the standard form of the Fourier series. So this comes up a lot, and we'll spend quite a bit of time looking at this. And if you want to relate the lowercase AKs to the capital AKs, the way to do that is the equations that are written here, here, and here. So one thing I want to note is, again, that what we saw before is if we have a signal x of t, and the signal is real valued, meaning it doesn't have imaginary parts, which is all the signals we've been looking at so far. They've all been real valued signals. Then the AKs, so if we have A of plus 5, that equals the A of, that equals a complex conjugate of A of minus 5, right? And vice versa. So that's just written written below. So the AK and the minus AK are related. Just one is the complex conjugate of the other. So I'll just say quickly, this idea that you could take any signal and represent it as a sum of sinusoidal signals, that was a kind of a breakthrough mathematically. And this was Joseph Fourier who made this breakthrough. And there were a number of people that didn't believe it at first. A very kind of interesting story about how he developed this. Okay, so he was a French guy, and that was sometime around 1760, right? So 250 years ago. All right. So we've written these out, but now let's talk a little bit more about what it means. Okay. So say we have some signal, some periodic signal. I've just drawn a periodic signal below, right? It repeats every t seconds, looks exactly the same. Then the question is, how do we find the AKs, right? So that this equation here is true. How do we find the AKs so that this is true, right? Remember, our goal is to design these AKs. And the reason we would do this is, we saw in the last few lectures how we would make the spectrum of a sum of sinusoidal signals. Now, if we have a signal that's not easily representable as a sum of sinusoidal signals, then how do we design these AKs so that we can represent it as a sum of sinusoids? That's the question at hand. If we're given a signal x of t and it has some form that's not just a sum of sines and cosines, how do we find these AKs for arbitrary xt's? And the answer is, well, it's just written right here, and we're going to spend most of this lecture proving this. Okay, so each AK would be given by the following integral formula, right? And the things that arrive here, right? So the k, right? That's the index of the coefficient. That's the coefficient in the Fourier series. And then 1 over t naught. T naught is, again, the fundamental period, right? So t naught, I guess I should have written up here, t0. Right? The signal repeats every t0 seconds. And then this integral is evaluated from 0 to t naught, so over one full period. Right? And that's the integral of x of t, the signal itself, and then multiplied by a complex exponential. Right? So that's how we come up with the Fourier series coefficients. So it might seem a little mysterious at first, right? But let's just kind of focus on this term up here, right? This equation here, right? And that's really all we're saying, that with these harmonically related frequencies, we can represent any signal as a sum of complex exponentials. And how we design the coefficients in that sum is just given by this equation here. All right? And then once we're able to do that, we can really take any signal and then we can arrive at the spectrum here. Right? And this is done slightly different on a digital computer, but this is the mathematical tool we're going to develop to understand how you would even begin to come up with this spectrum shown here. All right. So again, a lot of times we'll be given the following problem. We'll be given a periodic signal x of t, and then we'll be asked to find its Fourier series. And to do this, we must determine the coefficients a sub k. That's what our goal is when we're asked to find the Fourier series. It means find the coefficients ak for k ranging from minus infinity up to infinity, where k is an integer. All right, and we can just simply compute these using this integral equation that we just saw on the last page. All right, so all we have to do is, given that signal x of t, we plug in that x of t here, evaluate this integral, and then that gives us all the different AKs. So we have to evaluate it for a lot of different values of k, right? Or just evaluate it with k undefined, and then we're given each k. We can just evaluate the result for a particular k. All right, and that, again, the things in here are t naught, that's the fundamental period, and f naught is 1 over t naught. All right. So I don't want you guys to just, kind of take my word for this definition, right? I think it's important that we actually go through this and verify that this integral equation, right, this one here, if we were to plug that into the definition for x of t down here, that we would indeed get x of t back. So what I mean by that is, and for example, another approach to do this, there'd be two ways to verify this. One that we're actually going to do here is we're going to plug in now x of t, right? This is our definition for x of t represented as a sum of complex exponentials. We're going to plug this x of t into this integral equation right there, right? And then we're going to evaluate that and confirm that when we plug x of t into here, we indeed get ak back, right? And so we're just confirming that ak does indeed equal ak. And this is how we would verify or prove the Fourier integral equation and make sure that it lines up with the Fourier series equation. Okay, so let's do that. And this is really not too bad. It looks a little daunting at first, but if we remember the Fourier series integral equation, that's just written right here, right? That was what we saw on the last page. That's this whole line, right? And we have x of t can be represented, of course, it's this what's written in red here, all of this stuff. So we're just plugging this into the Fourier series integral equation, and now we're going to start manipulating things. All right. So the first thing that we're going to do here is we're going to exchange this sum, right, and this integral here. And in general, you have to be careful doing this, but these are relatively well-behaved functions, so just take my word for it that we can exchange this sum and this integral, okay? And then we get to the line below. So let's think about this for a second here. So what's happened between this line and this line? Well, the first thing that happened is we exchanged this integral and the sum, right? And then we also, since the integral doesn't depend on the coefficient L, we're able to bring this a sub L outside, right? And that ends up here, okay? And so then we're left with what I have, written as equation 1, right? And that's just an integral, right? And that integral depends on it's an integral over time from t equals 0 to t naught. And it also depends on a number of things. It depends on L, right? Where L is this, we're taking this sum over L. And it also depends on K. And K is the index of the coefficient that we're computing. Okay, so we're going to focus on, next let's focus on only equation 1, right? So equation 1, I can just rewrite this as by just combining these two exponentials, combining this one and this one, I can just rewrite it as we have here, right? All we're doing is we're factoring out the j2 pi f naught t from both of these complex exponentials, and then we're just left with this L minus k. So the first thing I want people to notice is that if L is actually equal to k, right, then L minus k is 0. And then the complex exponential is just 1, right? So if L minus k is 0, right, that goes there. E to the 0 is 1. And so we're integrating 1 from 0 to t naught, and that should just give us t naught. Okay. Now the next term is a little tougher, or the next scenario is a little tougher. And that's when L is not equal to k. So when L is not equal to k, we actually need to spend a little time evaluating the integral. All right. And it's in exponential, so we can use the chain rule, and you can all verify that when you integrate e to the something, right, we just get that rule from chain rule, the chain rule, we get that e to the something as a result, and also multiplied by 1 over what was inside, okay, the derivative of the inside, the quantity that's in the exponent, okay. So if you don't remember that, it's good to go look back at your notes from Math 222 or whatever calculus course you took, just to make sure that you can confirm that integral. And then that's of course evaluated from 0 to t naught. Okay? So when we evaluate that from 0 to t naught, now we're just plugging in first when t equals t naught. That's this first term here. And then the second term when t equals 0, right? Again, we have e to the 0, and that's just going to give us it should give us a minus 1 somehow, right? Because we're subtracting that initial value, right? And then we're left with what was out front, which is 1 over 2 pi f naught k minus L. Okay, so what's happening here is that we have in this term, remember k is not equal to L. Okay, so we have this is always some integer. It's just an integer. Maybe it's minus 5, maybe it's 7, right? But whatever it is, regardless, this f naught and this t naught, those cancel each other. Okay, so we have e to the j 2 pi times an integer, and that always equals 1, right? Remember, because these complex exponentials are periodic with period 2 pi, so anytime we input an integer in this kl for k minus L, then we just get positive 1, right? So this quantity is equal to 1. So we're left with 1 minus 1, and of course that equals 0. So there's these two scenarios. There's one when the index L equals the index k, and then we get a value of t naught, right? And then there's the other scenario when L is not equal to k. After just a little bit of work, we show that that integral is 0 anytime L is not equal to k. So what we have, right, is written at the top of the screen. We just confirm that integral, this integral 1 from the last page, takes on two values. It takes on the value t naught when L equals k and 0 otherwise. So what were we trying to do in the beginning? We were trying to show that here, this was our definition of AK. We wanted to show that we could just plug in what we used to represent x of t, and then we just get back to AK, confirming the Fourier series, right? And let's exactly do that. This is what we had written first, and then we plugged in what x of t was, and then we exchanged the order of integration and the sum. And what happens here now is we can break this sum into two parts, right? We can sum over the values of L not equal to k, because we know this integral always takes on the value of 0 anytime L is not equal to k. So we set this integral to 0 for any term in this sum where L is not equal to k. So this whole thing goes away. And then what we're left with is the term where in the sum, where L is equal to k. And when L equals k, right, this integral here, that equals t naught. Right? So we're left with, let's see if I have this written right. We're missing 1 t naught. We're left with 1 over t naught from out front. We're left with we're left with t naught from evaluating the integral when L is equal to k, when k equals L. And those cancel, and we're left with this AK, right? Because when in the sum, when L equals K, A sub L is just A sub K. All right, so we did indeed confirm that if we just plug in the two definitions into each other, we actually can get back the coefficients. All right, and if that went a little bit fast, it's really good to actually sit down and write this out, because the tools in doing this and seeing when the integral is this number 1 is 0 and when it's t naught is actually really fundamental. We'll need to do that to figure out and evaluate Fourier series. So this is an actual very good exercise to go through. So if it wasn't clear, maybe take a little time, maybe 20 minutes, and try and think through this exercise and try and replicate it on your own and confirm that indeed the Fourier series integral formula and the representation formula, they actually line up. Okay. All right, so let's do a really simple example that we kind of already know how to do. We already know how to draw the spectrum of x of t, but let's kind of make sure that looking at the Fourier series of x of t will give us that same spectrum, right? Kind of validate what we've been doing for the last 2 weeks. So normally the way you would go about finding the Fourier series of something is as follows. The first step you would do is calculate what f naught is, right? What the fundamental frequency is. And so here that's really, it's trivial in this simple example when x of t equals cosine 50 pi t, right? The fundamental frequency is 25 hertz and the period is 1 over that frequency, right? Which is so 1/25th of a second. And then the next thing normally that you would do is you would just calculate the AKs using this integral formula for the Fourier series coefficients. All right, here's the interesting thing about just a simple sinusoidal signal. Well, right, we know that we can write that the goal is to write the signal x of t as the sum of potentially infinite number of sinusoids, right? So from k equals minus infinity to infinity of a sub k e to the j 2 pi f times k, so f naught, right, times k times t, right? That was the Fourier series expansion. And we know that we can write cosine as, using Euler's identity, of 50 pi t as 1/2 e to the j um, 50 pi t plus 1/2 e to the minus j 50 pi t. Right. So this is an example where we can just kind of do this by inspection. Okay, so we'd say, what are the values of AK such that we can write this sum and just get down to what we know the cosine is using Euler's identity. So where, again, this f naught, this is 25 hertz, right? So let's just kind of guess, and then we'll check to make sure everything is correct. So let's say AK equals, for k equals 1, right? Say AK equals 1/2, right? And write that here. It's kind of guessing, and I already know what the answer is. So when k equals -1, let's also say that AK equals 1/2. And then the third thing is, say AK equals 0, otherwise. All right, now let's go back up to this formula, this one here, and let's plug in these values of AK and evaluate the sum. So we really only need to evaluate two terms in the sum, right? The first term being at k equals 1 and k equals minus 1. Right? All the other terms are 0. So maybe just write that to be clear. So the sum, so k not equal to 1 or minus 1, is just going to be 0 times the complex exponential e to the j 2 pi f naught kt. That's just going to be 0, right? So we just erase that all, erase what I had written. And then we only need to evaluate the terms in the sum of k equals 1 and minus 1. Let's do that. So AK, when k equals 1, is 1/2. And then this exponent, the exponent here, is just e to the j 50 pi t, right? And the second term, when k equals minus 1, we also have 1/2. So it's plus 1/2 e to the minus j 50 pi t. And again, I'm just plugging in the second term. So we did k equals minus 1 and k equals 1 up here. We just came up with these two terms here. And lo and behold, right, this is equal to cosine 50 pi t. So this was the short way of finding out what the Fourier series coefficients were. We kind of just guessed at what the answers were, right? We guessed that somehow AK would be given by what I have here, and it only has two terms. And indeed, that's the case, right? So you might say, well, this example is a little silly, right? We tried to set out and say we can represent this signal that's just a simple sinusoid as a sum of simple sinusoids. And that's an obvious kind of trivial statement, but it just allows us to kind of think through how these things play together. So in general, and what we'll spend a fair amount of time doing next time, is looking at how we can actually use this integral formula to evaluate more interesting signals that can't just be written as a simple cosine.